What's up guys and welcome to this new video about implementing and visualizing an algorithm in an Android application. 2 days ago I already uploaded a video about the bubble sort algorithm, which is more of an easy one. In this video we're gonna have a look at the merge sort algorithm, which is more complex when it comes to implement it and also how to visualize it on the UI. Let me quickly demonstrate you how this will look like when we have finished the application. When I click on Start Sort, the algorithm starts and it's a divide and conquer algorithm, so it breaks down the array to multiple smaller arrays until they are trivial to sort, and then they get merged together again. We will go through this step by step when we implement this algorithm, but now you can see that we have an initial array of 8 values, and then some steps happen, and at the end the array is sorted. And the merge sort algorithm is way better than the bubble sort algorithm when it comes to time complexity. And yeah, this can be a lot of fun and also helps to understand such an algorithm because the merge sort algorithm has a recursive variant which we implement here. And recursive functions are not always that easy to understand, but such a visualization can really help to understand it better. Alright, okay, I'm in an empty Jetpack Compose project. The only thing I did was to add these two colors for the background and for the button later. You can also use them from my GitHub repository, which is linked down below, or simply use your own ones. We can then straight start with implementing the algorithm, and such an algorithm is business logic. So it belongs to the domain layer. We will make a little packaging here. And for that, we go to the root package and create a new package called domain. In our domain package, we will have another package called model, where our business models are into, which are normally just data classes. Sometimes they have a little bit of logic, but not that much. Most of the business logic will be in use cases. So we will create this packaging structure, press enter, and in the model package, we can then create our sort info model, which will be a data class. It has an ID of type string, a depth of type integer, because later we will have a recursive call and we need to know the current recursive depth. I will also explain what a recursive call is in case you don't know that. So just leave it like this and we will come to this part later. Then we have sort parts of type list of type integer and sort state of type sort state, which will be an enum class. We define this here. Sort state, which takes a value of type integer, and the two types we have here is on the one hand divided, and this takes the value 0, and merged, which takes the value 1. So don't forget the comma. And later we need to differentiate between these two enum class possibilities, because in the algorithm we have a phase where the values or the array gets divided, and in another phase they get merged together again. And for the UI we need to differentiate between them to show the right values on the right place. Now we are already good to go to write down the algorithm. Let's go to our domain package and create another package called use case. In this use case package, we will create a Kotlin class called merge sort use case. The first thing we need in our merge sort use case is a sort flow of type mutable shared flow of type sort info, the data class we just created. This flow allows us to emit values over time, and we will emit values of type sort info at the right places inside our algorithm, and then we manually delay the algorithm's execution time so that it does not get processed too fast. And this allows us to see on the UI always what's currently going on. We will make our use case a suspend operator function invoke, because then we can just call this use case later like a function call. This does not have to be an operator function. You could also call this function start or execute, and without this operator then. This function will take a list of type integer and also a depth of type integer, and it will return a list of type integer. Then we can delay this function by 500 milliseconds and emit our first value. I will explain the merge sort algorithm in detail, but let's just set this up a little bit. The first emit will be sortflow.emit sort info, And for the ID, we will pass uuid.randomuuid.toString. I'm not pretty sure if we actually need this ID. This was in a previous version where I tried around with different animations, but that didn't work. So I think this ID is not useful anymore. Let's just keep it and don't care about it. Then we will pass the depth, which we get passed from above. The sort parts will be our lists, and the sort state will be sort state dot divided. All right, okay. The only thing you need to know right now is that when we invoke this function with an integer list and corresponding depth, then we just emit these values and also provide this divided information. After that, we can check on the list size. We will say val list size is equal to list.size. If list size is less or equal than 1, then we can return the list. Because this is the easy case, this is the trivial case where the list just contains one element and this list is already sorted. So we can return this sorted list with one element. If this is not the case, then we need to split up the list in two equal parts of the list. We will say var left list is equal to list.slice 0 until list size plus 1 divided by 2. And then we have also the right list, var right list is equal to list.slice list size plus 1 divided by 2 until list size. These two variables now contain the left part of the list and the right part. In case the list has an odd number of elements, the left list has one element more than the right list, but this doesn't matter. Also, the right list could have potentially one element more and it would also work. I will just put a simple comment here to show you this by an example. If we have a list size of 13, for example, then this would result in a left list of 0 to 6, and the right list would be from 7 to 12. In case the list would be of size 14, then we would have also 0 to 6, and this time 7 to 13. So these are 7 elements, and these are 7 elements, and here we have 6 elements and 7 elements. You can check this out. You can just put the values into this list size and check this calculation. This should split up the list in two equal parts, and in case it's odd, the left list has one element more. And now the most important part comes when we apply the recursive call. We will say left list is equal to this, so this function here, we will invoke this function again within this function. This is a recursive call. We also get that indicated by this little sign here on the left, and we will pass the left list and say depth plus 1, because when we are dealing with recursive calls, when we invoke a function inside the function itself, the depth starts to increase. And then we also do this for the right list. We will say this and pass the right list and also say depth plus 1. Okay, now let's take a quick example to understand this recursion a little bit better. We can remove these two comments that we get everything on the screen. Let's assume we will invoke this function, this merge sort function initially with a list of size 4. We will say size 4 and the depth will be 0 by default. And then we invoke this function the first time. It gets delayed by 500 milliseconds and also the information gets emitted via this shared flow. We don't need to take care of these two operations. They are not important to understand the algorithm, so let's just ignore them. Then the first important thing that happens is the check if the list size is actually less than 1 or less or equal than 1. And this is not true because our initial list is of size 4. Then this list gets split up into two lists, in the right list and the left list. The left list contains 0 to index 1. The right list contains 2 to index 3. So they are equally split into two lists of size 2. Then we invoke this function again with the left list, so that this function gets invoked again with a list of size 2. And then everything happens from the beginning. The check if the list is actually less than 1, This is again not true since we pass a list of size 2 now, and this list of size 2 gets now split up into a left and right list, and in this case the index of the left list will contain, or the left list will contain the index 0 of the original list, and the right list the index 1, and then this gets called again, and this time this check is true. And this will just return the list because the list does only contain one element and is trivially sorted. So it's not that important yet to understand why we initialize this left list with the result of that and also with the result of the right list. It's only important for you to understand that all that does right now is to split up the lists in equal parts and do this as long as everything is split up. It's also really important to understand that this initial call of the function with list of size 4 needs to wait until the result of this function call is there and also the result of this function call. And when we pass a list with size 2 into this recursive call, then it gets an own function scope with list size 2, which also needs to wait for its own recursive function call. So it's really important to understand that when it comes to recursion. This also means that our initial function call with list size 4 gets executed first, but finishes as the last function, because it needs to wait for its subfunctions to finish, and they need to wait for their subfunctions to finish. This is how recursion works. If you are still confused, this doesn't matter, because later, when we visualize this algorithm on the UI, you will see how this list splitting actually works. And right now we have still a compiler error because we need to define the return type of this list. We need to somehow put this together now, and now the second most important thing about this merge sort algorithm comes, the merging function. It will be a private suspend function as well. Merge, it will take a left list of type mutable list of type integer, a right list of type mutable list of type integer, and the depth of type integer as well. And it will return a list of type integer. Then we can invoke this merge function from our main function. We will say return merge, and we will pass the left list to mutable list, then the right list to mutable list, and also the depth. And then our compiler error is gone in our main function here, and we need to take care of the merge function. Let's have a look at a quick example what this merge function could potentially do. When we have a left list up here of size 1 and a right list of size 1 because the previous list was of size 2, then this gets passed into the recursive function, into the recursive call. And since this just returns the list, if the list size is less or equal than 1, this would result, this left list would result the same list which gets passed into the recursive function call. And the same thing for the right list. So they are then initialized and the function can continue to work because there's no subfunction which needs to be executed first, because the subfunction actually returns a list. Then the merge function can be invoked with the left list and the right list. And since these two lists are of size 1, it's trivial to compare and to sort them. And later, merge get also invoked for lists of size 2, of lists of size 4, and so on, with the knowledge that these two lists are already sorted. Let's repeat this again, because this is also really, really important to understand. When we invoke merge with lists of size 1, it's actually trivial to sort them because each list itself, the left list and the right list, are actually sorted because they only contain one element. Then merge returns a list of size 2, which is actually sorted. And this left list and this right list, one level higher in the recursion, gets initialized or gets set to this list of size 2. Then merge again gets called with the left list of size 2, the right list of size 2, but with the knowledge that these two lists are actually sorted. And after that, it gets invoked with list of size 4 and right list of size 4. and they are also sorted, and this will result in a list of size 8, which is also sorted, and so on. And the recursioner, which splits up the lists, makes sure that this merge function gets called at the right moment. The first time when the lists only have size 1, and the last time when the lists are actually sorted and have the size n divided by 2, and this will then result in our final list. Okay, alright, enough talking. Let's go to our merge function with the knowledge that the past lists are always sorted. We can say, well, merge list is equal to mutable list of type integer, and this does not contain an element because we need to fill this merge list. Then we say, while left list is not empty and right list is not empty as well. As long as this is the case, we can execute or we can sort and create the merge list. Then we will say if left list dot first, which should be the lowest element in the left list, is less or equal than right list dot first, which is the lowest element inside the right list. If this is the case, then we say merge list dot add at the index of merge list dot size the left list dot first item. We can achieve this with remove first. This will return the first element of the left list and also removes it. If this is not the case, then we do the same thing for the right list. We can copy and paste this here and change this left list to right list dot remove first. Let's also take a quick example for that. Let's assume we have the left list with 2 elements, and the first element is 3 and the second element is 7, and we have a right list with the first element 2 and the second element 5, for example. So both lists are actually sorted. Then when we go in this while loop, this is of course true because left list is not empty and also the right list is not empty. Then we check if left list dot first is less than right list dot first. This is not true because the right list's 2 is actually less than the left list's 3 as the first item. Then we go into this else branch and we add at the merge list. Let's also indicate this or show the merge lists in this comment. The merge list is actually empty, and we add into the merge list the right list dot first item. We will append this here in the merge list and remove it from the right list because this remove first will also remove the item, and then we continue in this loop. We will again check if left list dot first is less than right list dot first, and this time it's true because right list first is 5 and left list first is 3. So we go into this one, and this means that we remove the first item of the left list and also append it inside our merge list. So in the merge list the 3 comes and it gets removed from the left list. After that, another loop. We will again check if the left list dot first less than right list dot first. This is not true because the 5 is less than the 7 of the left list. So we go into here. We will remove the 5 of the right list and append it to our merge list. And now we have the case that this condition check is false because our right list is now empty. So the while loop is over, but we still have one element left, which we need to add into the merge list. And for this simple case, we say merge list dot add all, and we pass the left list, and we will also say merge list dot add all for the right list, because it could be also happen that the left list is empty and the right list contains an element left. And then the left list remains with this 7 as the last item. This is okay, we don't need it after this add all call, but the merge list now has all elements and the merge list is sorted. And now you can imagine that this works anytime. It works always when we pass 2 actually sorted lists inside this merge function and merge them together. Alright, okay, this was it for the merge function. We only want to also emit this sort info for our view modulator so that we can also show the merging steps on the UI. We will first delay this by 500 milliseconds again, and then we can say sort flow dot emit, and we will again emit the sort info. For the ID, we will pass uuid.randomuid.toString. The depth will be the passed depth. The sort parts will be our merge list. and the sort state will be this time sort state.merged. And the last thing we need to do is to return our merge list actually, and then all compiler errors are gone. And this is actually the merging sort algorithm, or also called merge sort. Now we can take care of visualizing all the steps we have here on the UI. Let's close the domain layer, and we can also close this UI and create a new package from our root package called presentation. There we will have another package called state, and in here we will have a data class called sort info UI item, which will have some properties which helps us to define what we should show where on the UI. We have a val ID of type string, val depth of type integer, val sort state of type sort state, val sort parts of type list of type integer. You will see what I mean by this later. And then val color of type color. Let's collapse this state folder and create our view model. We will call this sort view model, which will be a class. And in the constructor of this view model, we need to get access to the merge sort use case, and we can straight initialize it here. After that, we can take care of the important vars, var list to sort, which we will initialize manually. Normally, you would retrieve a list you want to sort from the database or from the network or from a sensor. Here we will just initialize it with random generated ones. We can do this in the init block of the view model. For I in 0 until 8, we will initialize it with 8 values. Then we say list to sort dot add, and we want to add values from 10 to 99 and say dot random. Then we will define our state, which will be a var sort info UI item list, which is equal to mutable state list of type sort info UI item. And after that, we will define our function start sorting. First, we want to clear the sort info UI item list, because later we can then click on the sort button multiple times to start the sorting again. So we will first clear all the items. And then we will say view model scope, and I again forgot to inherit from view model like I did in the last video. So now we can get the view model scope dot launch, and we will invoke the merge sort use case with our list to sort, and for the depth we pass 0 by default. Now we need to subscribe to all the emissions from our use case regarding the sort info state. We can call a function called subscribe to sort changes, and we will define this function now. This will be a private function, subscribe to sort changes. This function will have a job, and first we need to define this job. This has also the background that we can cancel this job and start it again, so that the collecting of the data stops when we start the sorting again. This will be a job of type job, which is optional by default, and we will set this to null. Let's import job, and here as the first call we can say job.cancel. After that we will initialize the job with viewModelScope.launch, and in here we can say merge sort use case dot sort flow dot collect. That means we collect all the values that the merge sort use case emits, so each step of the algorithm. And now things will get a little bit complicated when it comes to arranging them the right way, because we have different depth levels. We have also divide state and merging states, and we want to arrange this in kind of a tree structure later on the UI, and therefore we need to arrange and sort the items so that we can achieve this, because when we have the recursion, the emissions of these recursions needs to be put in the right order. First, let's call this provided values sort info, and then we need a value depth already exists list index, which we can get from sort info UI items list index of first. And for the predicate, we will pass it.depth is equal to sort info.depth, and it.sortState is equal to sort info.sortState. This checks if in our sort info UI item list is already an element which has the same depth than the new sort info depth, and also the same sort state that we get provided from the sort info sort state. If such an element does not exist, the easy part comes. So if depth already exists list item index is equal to -1, because this index of first will return -1 if the given predicate is not matched by any element. Then we can say sort info UI item list dot add, and we will then add a sort info UI item. For the ID, we will pass UUID dot random UUID dot toString. For the depth, we will pass sort info dot depth. For the sort state, we will pass sort info dot sort state. And for the sort parts, we will make a list of sort info dot sort parts. And later on, if this is not equal to -1, if the element already exists, we need to modify the sort parts list. We need to append to this list additional sort parts. You will see what I mean by this later. Then for the color, we will just pass a random color. We will say 0 until 255. Let's also import column dot random. Then we can copy this and paste it 3 times. The second color will be, or the blue part of this color will be only go to 200, and the green part as well. And I think we imported the wrong color here. Let's go to the top and remove this graphics color. We need the compose color. Then we can import it again, the compose one. And for the alpha, we will pass 255, and we still get an error. Why is that? Because we still have the wrong color imported. Let's remove this here. Oh, okay, I see. We need to remove this color from the sort info UI item and import the compose graphics color here. And now we import it here as well, and then the error is gone. Sorry. Then down here in the else branch, when the item already exists, we will say, well, current part list is equal to sort info UI item list, and we will pass the index because we know that it exists if we are in this else branch. Let's also put this in a separate line, and then we say sort parts to mutable list. And I hope this is still readable. Yes, it is. Then we say current part list dot add sort info dot sort parts. So we will append to this sort parts additional sort parts when we are in the same depth and when it has the same state, like dividing or merging. So later, when we see the algorithm work, that on the same depth in the merging part, for example, different lists are listed in a row next to each other. This is what this list here is about, or let's better say this list. This is just a temp list. And after that, we can say sort info UI item list dot set, and we will use the depth already exists list index sort info UI item list at the index of depth already exists list index dot copy, and we will pass sort parts our current part list like this. And we get a warning here because we can use the indexing operator. Let's put this then in a separate line so that it's readable, and then we are good to go to continue. The last thing we need to do is to sort our sort info UI item list by the sort state and by the depth, so that we can list it depending on the merging or dividing state and also depending on the depth. We want to start with all the dividing steps from depth 0 to depth 1, 2, and 3, and then we want to list up the merging state steps from depth 3, 2, and 1, because the depth is inverted. You will see this when we display it in the UI. I think this will take another 5 minutes, and then we are good to go to try this out. We can say sort info UI item list dot sorted with, and there we need to pass a comparator. We will say compare by, and for the first argument we will pass it dot sort state, and for the second argument we will pass it dot depth, and then we are good to go to create our UI. Now we can go to our main activity and remove all this default stuff and also this one. And I think we can set up the UI in the main activity. Normally you should do this with a separate screen, but for this tutorial it's fine. We can start with a box, and this box will take a modifier which fills the max size, sets the background to gray, and also applies a little padding of 10 dp. This box will have a content alignment, which we will set to alignment.center. Let's import this DP and open the box scope. In here, we will have a lazy column, which takes a modifier as well. This modifier will also fill the max size, and the alignment will be alignment.top-center. For the vertical arrangement, we will say arrangement.space by 30 dp. And for the horizontal alignment, we will say alignment.center horizontally. Then we can open the lazy column and we will say items indexed. And these items come now from our view model. And first we need access to our view model. We can initialize it up here. We will say private val sort view model by view models, and we will pass for the type sort view model. Then we can go back to our items indexed and can pass our sort view model.sortInfo UI item list. Open this lazy column scope. In here we will get access to the index and also to the, well, let's call it item, and this will be of type sortinfo UI item. Okay, well, let's just call it like this, sortinfo UI item. And first of all, we need the depth parts is equal to sortinfo UI item dot sort parts. Okay, let's try to understand this a little bit better. We pass the sortinfo UI item list, which actually indicates, or the size of this list indicates how much steps we need in our algorithm, how much deepness levels we have. And this lazy column will go over each of these items. And each of this item has also different sort parts. And these are this sort parts, so that they get listed next to each other on each specific depth level. And each of these sort parts has also multiple values, which needs to be listed up in a row. I hope this gets a little bit more clear when we actually have a look at the UI. You can also try to understand this on your own, because, well, if I would have a look at this code with nested lists and all that stuff, I wouldn't understand this immediately either. In here we can first check if the index is currently 0, so we are the first item. Then we can also append a label or show a label that we are currently dividing. We can achieve this with a text. The text of this text will be dividing, and the font weight will be set to fontweight.bold. The color will be equal to color.white. The font size will be set to 26 sp. The modifier of this text will be modifier.padding, and for the padding of the bottom we will set 20 dp, and we will also fill the max width. And after that we also apply text align is equal to text align.start. The next index check will be for our merging label. We can just copy this text and paste it down here. This time we will check for the index is equal to 4. When we have a list of 8, then at the index 4, merging always starts. We could also calculate this depending on the list size, but I think for the demonstration here, this should be fine. I won't do any more calculations now. The video is already quite long. For the text, we will say merging. Below this if check, we will have a row with a horizontal arrangement, and this arrangement will be set to center, and the modifier will be set to modifier.fillMaxWidth. This row actually is a row which we will have for each depth level. We can open the row scope, and in this row we need to list all the different sections of this row or parts of this row, which we can get from our depth parts. So for part and depth parts, we will list all the different numbers for each part. Let's assume that we divided the list to 4 lists of size 2. Then we have 4 different parts, and each of this part has 2 values to show, which needs to be shown together, but the different parts need to be separated from each other. And for that we can also use a row inside this for loop. The horizontal arrangement will be here, arrangement.spaced by 5 dp. The modifier will be set to modifier.padding, and we will apply a start padding, but only if it's not the first list item, so that we don't have at the left side also this padding, only in the middle of the different items. So start is equal to if depth parts dot index of part is equal to null, then we will apply 0 padding, and else we will apply 70 padding. The background will be set to sortInfoUIitem.color and the overall padding will be set to 5dp. Then we can open the row scope, and in here we will sadly have another for loop for number information. In part, these are the actual numbers we want to show. If part.index of number information is not equal to part.size -1. That means that we have not the last number to print and we only want to apply or append a dash line that we can separate the items, but we don't want to do this for the last item. In this case, we can say text. For the text, we will say number information and append this dash line. And we can also remove the curly braces here, of course. The font weight will be set to fontweight.bold. The color will be color.white. The font size will be set to 19 sp. If this is not the case, then we can simply copy this text and paste it down below without this dash line. Okay, alright, this was it for visualizing the algorithm. The only thing that's left is actually our start button, where we then start the algorithm to sort the array. We can do this below this lazy column scope, I think. We will apply a column here. The modifier will be set to modifier.fillMaxWidth. The background will be set to gray. The padding will be 15dp. The align will be alignment.bottom-center. Then we can open this column scope, and because we have this arrow, I think we are in the wrong position. Let's try it here. Yes, this should work now. And we also set a horizontal alignment to alignment.center horizontally. The vertical arrangement will be set to arrangement.space by 15dp. Inside our column, we will then have a text which shows the current array we want to sort. Sort viewModel.list to sort. For the font size, we will say 22 sp. For the font weight, we will say fontweight.bold. The color will be set to color.white, and then we only need the button where we actually start the algorithm. We will say button on click method, sort viewModel.start sorting, and for the text we say start sort. The font size will be set to 22 sp as well, and the font weight will be fontweight.bold. And sorry, I put this column in the wrong position. This is our item indexed scope. This is the lazy column scope. This is the box scope, and here the column belongs to. Now we can start the application and have a look if everything works. I will just put this a little bit more in the middle so that you can see everything. And now the dividing starts and also the merging happens. And I think we can see all the different steps in a really nice way. The only thing that's missing here are the rounded corners of the different depth items. Let's go to this background and change this to rounded corner shape of 10dp. Launch the application again and have a look at the visualization. Yeah, I think this looks better with rounded corners. And I think I can also go over the algorithm itself again and try to explain it. Let's go to our domain layer to use case, and this delays of 500 milliseconds, let's increase them to 2000 milliseconds so that it does not happen too fast. And yeah, by the way, you can see the list is sorted at the bottom. And yeah, let's launch the application again, maybe besides this algorithm. Okay, all right, I rearranged things a little bit, and also to make sure that you can see the code and the mobile phone and that my picture is not about the phone. And this function gets called with a list of size 8, which we can currently see on the mobile phone initially. Then this left list will be created and the right list will be created of size 4, and the function gets called again with this left and right list. And then it happens again. We have now lists of size 2 until we have lists of size 1. And then the merging starts. And you will see on the UI that only one part of this initial list gets divided, and then the merging starts, but not everything is divided yet. This is because this left list recursion call always happens first. And the right list recursion call can only happen after all the deep calls of this function are finally finished. When I click on start sort, you can see this is the initial list, then the left list comes, then the second left list, and then the third call of the left list, and then the right list finally, and also the merging starts then. And then it gets back both to the older function calls and executes them. And yeah, you should go really through this step by step to understand this a little bit better. But the core concept here is to divide the lists into lists of size 1 until they are trivially mergeable, and then they get merged back, and then they can be merged and merged together until the whole list is finally sorted. Okay, all right. I hope this was a cool video for you and you could learn something. I know this is not that easy to understand if you never have heard of it, but with such a visualization, you can really always know what's currently going on, and you can really understand difficult functions, difficult algorithms. In case you want to see more about such algorithms and the visualization of it, then let me know in the comments and maybe I will do a video about it.